To get us started, please welcome Jason Davis.
Hey everybody, I'm Jason Davis, Editorial Director at the Planetary Society. Thanks so much for coming to this session today. The Planet Fest 21 is all about the celebration of the arrival of these missions at Mars. We had 2 successful missions already. The United Arab Emirates Hope Orbiter is already there in orbit, as is China's Tianwen-1 mission. So that's fantastic. We just got 1 more to go, NASA's Perseverance rover. So we're all about Mars for this conference. However, we are the Planetary Society, and we have so many diverse interests in the solar system and all these great worlds we want to explore and all these awesome missions we want to do. So when we were asking for feedback on how to structure Planet Fest, a lot of you said, hey, we want to hear about worlds besides Mars, and we could not agree more. So we arranged this session, and for those of you who get our member magazine, 3 of the people in this session were authors on an article recently that looked at the next 10 years of solar system exploration and then talked about some of the exciting science that we're going to do and some of the missions that we have yet to, that we're looking forward to. So without further ado, I'll go ahead and introduce the rest of our panelists. We'll start with Deepak Srinivasan. He is an engineer and the Civil Space External Engagements Lead at Johns Hopkins University Applied Physics Laboratory. He's also the communications lead for NASA's Europa Clipper mission, and he has involvement in several other APL missions, including DART. There's another exciting mission launching this year to impact an asteroid, and the Dragonfly mission to explore Titan. Deepak, thanks for joining us. Next up, we have Maithri Bose. She is a cosmochemist and an assistant professor at the Arizona State University School of Earth and Space Exploration. She's on the steering committee of NASA's Small Bodies Assessment Group. And as she's going to tell us, there's a lot of cool small bodies missions that are about to get started here in the next few years. So Maithri, welcome. Thank you for joining us.
Thank you, Jason.
We also have Brett Daneby. She is a planetary geologist at the Johns Hopkins University Applied Physics Laboratory. She is currently serving as the deputy principal investigator for the Lunar Reconnaissance Orbiter camera, which we'll talk about here in a little bit. Takes all those awesome pictures from lunar orbit of the moon's surface. And she's the science chair for NASA's Lunar Exploration Analysis Group. And she also has an asteroid named after her. So that's pretty cool. Brett, thank you so much for joining us.
Yeah, thanks. This is really fun.
And last but not least, we've got Joseph O'Rourke. He goes by Joe. He's an assistant professor at the School of Earth and Space Exploration, also at Arizona State University. He serves on the steering committee of NASA's Venus Exploration Analysis Group. So, Joe, thanks for joining us to talk a little bit about Venus.
Thank you for having me.
All right, everybody, so let's jump right in here. I thought maybe we'd kind of start with the outer solar system and slowly work our way inward. So Deepak, let's start with you. You're working on 2 really exciting missions, Europa Clipper, Dragonfly, both going to moons in the outer solar system. And maybe you could give us an overview of those and what they're going to study on Europa and Titan.
All right, sounds good. So thanks, Jason. And thanks to all of you guys for joining in. So your participation in these kinds of events really help make all of these missions that we're talking about actually happen. So thank you for that. What you're seeing here is the depths of Earth's oceans. I wanted to start off here on Earth before we go out to outer space. And the reason I wanted to show this is why we explore ocean worlds. Wherever you find water anywhere on Earth, even in the most extreme environments, you always find life. Now here, what you're seeing is actually towards the bottom of the Mariana Trench here on Earth. So you're talking roughly, 7 or 8 miles of ocean above you. It's a lot. And talking about extreme environments, this area is denied sunlight, right? Because sunlight can't penetrate that many miles of ocean. This black smoke that you're seeing around here, those are called black smokers. Really, interesting name, but that smoke is not smoke. It's actually superheated water. And just the chemistry of the water is what gives it that black color, but it's superheated beyond boiling. But it can't boil because the pressure of all that water above is just incredibly immense. And despite the extremeness of this environment, just take a look at what you see. This is what we've found at the depths of our own oceans, places where you'd think that life has no business being, but yet there it is. And it's just quite remarkable. So that shows that even in the most extreme environments, wherever you find water on Earth, you find life. Now, Earth is not the only ocean world in our solar system. Jason mentioned we're starting out in the outer planets. So on the outer planets, you have all these moons, and a lot of these moons are considered to be ocean worlds. You see 5 of them here. We're going to talk about Europa and Titan. Now, when we talk about an ocean world, it doesn't look like a standard ocean like one would see if you went to the Bahamas and you were on a vacation there. What you see is an ice shell. So this is what we think Europa looks like. You have this ice shell, and then underneath that, you have an entire layer of water. And then underneath that water, you have rock and then perhaps an iron core. So this is what we think is on the inside of Europa. We're going to go there to try to find out. But just to give you guys an idea of how much water we think is out there, for Europa, if you look at just that shell of water, that layer of water, we think it's about twice as much as all of the water here on Earth. So all the lakes, all the rivers, all the oceans, all together, double that, you get this. And that's what we're hoping to verify at Europa. To amplify that even more with Dragonfly, when we go to Titan, we think there actually might be 10 times as much water on Titan as there is here on Earth. It's kind of astounding if you think about that. But anyway, so Clipper. We're sending a spacecraft. When I say we, it's a joint effort between the Jet Propulsion Laboratory, JPL, as well as APL. We're working together, and there's other universities that are contributing some of the instruments as well. And we are going to send what you see here, this spacecraft, to Jupiter, such that we can fly by Europa and really understand what's going on there. The goal of this mission, I want to make it clear to everybody, is that this isn't a life detection mission. It's not like Star Trek where we're going to go someplace and somebody says, "Hey, Captain, we see signs of life." This spacecraft is not going to be doing that, but it's going to test for the habitability of Europa. It's going to tell us whether or not the conditions there are suitable for life. And when I say conditions, there's actually 4 conditions that have to be met for life as we know it to be there. Water, and we talked about water just now. The right chemistry. We want to make sure that all of the right constituent particles are there to provide the organics necessary for life. And then there has to be energy. If you just have a bunch of ingredients and no energy, the ingredients just hang out. They don't really do much. So you need to have some sort of energy input. Now that can come from tidal heating. As the moon goes around Jupiter kind of tugs on Europa, much like the moon tugs on our own seas, and causes the tides. That kind of happens in an inverse sense over at Europa. So we want to look and understand that energy mechanism, as well as there might be some energy on the interior of Europa, much like the Earth has a molten core, and we get energy coming from we can get warmed up from the inside of Earth. We want to understand that part about Europa. So those are the 3 ingredients. And the last ingredient is really time. It needs time, like life needs time to happen. And if you think about Earth is about 4.5 billion years old, give or take a few million. And, it's not like life existed as soon as Earth formed. It took about 1 billion years. Earth was just, earthing along or so for 1 billion years until life was that spark was finally able to happen. So you need time. Now, the good thing about all these ocean worlds is that they are old. So the time is there, and we need to understand whether or not the other 3 ingredients have actually happened or are there. So I want to talk really quickly about the spacecraft. So this is a gigantic spacecraft. If you think about it, we're operating at Jupiter, right? And Jupiter is roughly 5 times further to the sun than Earth is. So in order to capture, so the sun is really small. And so in order to capture enough power, we need to have gigantic solar arrays. And to give you an idea of scale, if you've ever been to a basketball game, imagine a basketball court. Now, the wings of Europa, of the Clipper spacecraft from tip to tip is about the same length as a basketball court. So this thing is huge. So you can imagine launching something this large and operating it and pointing it exactly as it should to both get the science data as well as beam all that science data back to Earth. It's quite a remarkable machine. Right now, to give you an update, we're in what we call phase C of the mission. Phase C means we're actually building some of the flight hardware. And in fact, up the street a little bit from me at APL, I actually have engineers right now, this minute, testing some of the flight hardware. I'm in charge of the radios that are going to be flying on here, and it's in work right now. So it's really an exciting time for the mission. Just to give you a quick idea as to how the spacecraft works. Once we get to Jupiter, the hardest challenge that we have is actually the radiation. So Jupiter has a insanely large magnetic field. And because of that, as you know, the sun is constantly spewing out these charged particles. That magnetic field serves to capture those particles, forming these really intense radiation belts around Jupiter. And what happens then is that Europa, as luck would have it, is right in the middle of these radiation belts. So if we went to Europa and just sat there, we would fry. So instead, what we do is we go into a Jupiter orbit where we dive in, take a bunch of data, and then get out of there. And then dive in, take a bunch of data, get out of there again. And that's how we're able to look at Europa over time and see different faces of it without actually cooking our own electronics. So this is going to be a fascinating mission, and we're really looking forward to the data that we get back. If you think about it, it's going to be, as Bill Nye always says about this mission, it's going to be transformative. It can literally, he uses the words change the world, but here it's true. You think about how people's perceptions of life would change if we found out that indeed life can exist in worlds outside of Earth. Switching gears really quick, I wanted to just touch on Dragonfly. So what you see here is Dragonfly across a few different phases of the mission. So in a nutshell, really quick, so Dragonfly is our collective 4th New Frontiers mission, and it's being built here at APL as well. And the first question is, why do we want to go to Titan? So you think about what I talked about before when I told you Earth is 4.5 billion years old, and then roughly 3.5 billion years ago, the first evidence of life happened. So, before that, Earth was just a bunch of chemistry, and then something happened and Earth became both chemistry and biology. So here we have what we call prebiotic Earth. So Titan, what we think, actually exhibits what conditions on Earth were like just before the birth of biology. So you can see why it's an incredibly compelling destination to go to, so we can learn possibly about our own planet's history. The other cool thing is the landscapes that you see here. These are organic sand dunes. Titan is just a really cool place. It has, we talked about a subsurface ocean of water, but also it has a second ocean as well. On the surface, we have a whole lot of methane, and it's an entire hydrological cycle that exists. We have these methane lakes. The methane evaporates into methane clouds. Those clouds rain down methane rain, and that forms methane rivers flowing across organic sand dunes, filling up methane lakes again. So we have an entire cycle that we want to understand and learn all about. So that's why we're going there. And the reason that we're going there with Dragonfly. And the reason it looks like this, we've launched rovers before and gone on different planets rolling around because that made sense there. Here, we're going to be flying. And the reason that we're flying is not just because it's cool. I mean, it is really cool, but it's actually the best way of traveling on Titan. Now, Titan, the atmosphere on Titan is about 4 times more dense than Earth, and the gravity is 1/7 that of Earth. So it's actually really, really easy to fly on Titan. In fact, any of us, if we just stood there and flapped our arms, that would probably create enough lift for us to actually fly ourselves. So that's the reason that we're using this whole rotorcraft concept to check out Titan.
That's super cool, Deepak. Yeah,
Yep.
Sorry, I want to make sure we get on to everybody else. Is there anything else you wanted to stress? Yeah.
Yeah, that's all I have, and I'm happy to talk more during the question and answer. But we have a whole lot of other talks that are going to be really interesting. So,
Awesome.
Time to move on.
Yeah, really looking forward to both of those missions. Super cool. Well, let's move into the inner solar system a little bit, and I'm going to kick it over to you, my3. I would say moving inward towards the asteroid belt, but really we're talking about small bodies and small worlds, and that's one of them. That's what you study. And that can really mean a lot of things. And when we say small worlds, I just thought maybe it would be helpful if you started us off by talking about what do we mean when we say small bodies, and why are these little worlds so important to study?
Yeah, that's a good question. So when we talk about small bodies in our solar system, we literally mean small. So objects that are not planets, not dwarf planets, primarily asteroids and comets that we can identify either in between planets. So, in between Mars and Jupiter, we have the main belt, and there's lots of these small bodies there. There are ones that are also beyond the orbit of Neptune, and those are also smaller. So again, the initial definition is just the size. So it could be 10 meters to about 500 kilometers or so in size, and they have irregular shapes. Having said that, there are some moons or satellites of planets that are also sometimes spoken to as small bodies. And so we look at their orbits, if they're irregular in shape, all of that information can be used to say whether they're small bodies or not. The best thing is that, there's a common.
Just showing our audience as you're talking here, I put it up on the screen. These are a bunch of small worlds compared by size to check out. Please go ahead.
Yeah. So, the best things come in small packages, right? And so these small bodies can tell us so much about our solar system, its history, how planets formed, why the planets look the way they do. Deepak was talking about the different, larger bodies, and the surfaces look so different from one another. The atmospheres look so different. And these small bodies, we think, are the first bodies that formed, that collided, accreted to form these larger planets. And so if we can understand what the compositions of some of these small bodies are, what the diversity in these bodies can tell us about the planet formation process, we can understand planet formation, right? So that's pretty much, I think, the main aim for a lot of us here in the panel and the community. These small bodies, so they retain a record of the conditions in the early solar system. They can tell us about the processes that were going on, what kind of collisions were going on. But also there's been some rearrangement of these planets. These planets were not static in one place, right? As they were growing, they were moving around. And some of these small bodies have an imprint of that. They show signatures of that. Some of these small bodies are large-ish enough that they go through this period of differentiation. So as you know, Earth is a differentiated body with a core, a mantle, and a crust, right? And some of these small bodies have gone through this partial differentiation process. And that's kind of important for understanding their further evolution. So like Jason said, I am on the steering committee of NASA's SBAG, which is the Small Bodies Assessment Group. And we lay out in a document, the overarching questions that our community wants to work on, the small body community wants to work on. And pretty much we want these bodies, as you can see in the schematic, I mean, they're so diverse, right? And each of them is telling us something, a story of its own, something really important, a key piece in the evolution of our solar system. We also can then sort of get a peek into the processes that are going on in the bodies themselves. And that could be, lots of these bodies are constantly bombarded by particles, ions, electrons, right? How do these processes affect the surfaces and change it, modify it, such that when we send a spacecraft, we see these changes in the surface compositions as a result of these surface processes. And then, of course, like I said before, one of the main questions that we want to answer is, why is Earth so special? Why does it have so much more water on its surface compared to some of the other planets? Mars, we think, did have some water, and there's lots of evidence of that, right? So what changed? So this question of how Earth got its water inventory, why it retained it, what are the different kinds of small bodies that provided water to these planets? These are some of the really big questions that I think the small body community can help answer. So yeah,
It's very cool. They're kind of like time capsules for DB that show us what the beginning of the solar system was like.
Right.
Could you also talk about some of the upcoming missions that we have to some of these? One of which, if I'm not mistaken, is launching this year. Might have that wrong. Well, if we're talking about DART, I guess. But anyway, could you talk about some of the upcoming missions to small bodies worlds?
Yeah, so I think maybe the community knows about both the OSIRIS-REx mission, which is to an asteroid Bennu, and then there's this, so that's a NASA funded mission, whereas there is a Japanese mission to another asteroid, Ryugu, and both these asteroids, they actually look very, very similar. In terms of sizes, there's slight differences, but the way we think they formed is quite similar. And as a result, they have a shape that's similar. And we're going to have samples from both these asteroids very soon. I don't know if Deepak wants to talk more about the DART mission, since I don't know if he's involved with that mission and he wants to say something. But yeah, so Deepak, did you?
Oh, we'll save that for the Q&A. So let's give everybody a chance to talk. But yeah, we'll be happy to dive into DART. It's a very impactful mission. So anyway, it's a bad joke.
Okay, yeah. So I didn't know exactly which mission you were talking about, Jason. The one this year. Whoops.
Oh,
It looks like he lost his audio. I think he might have been referring, there's a couple of discovery missions that are coming up, both Lucy and Psyche, that are going to asteroids in the upcoming years. I don't have the launch dates off the top of my head, but yeah, small bodies are definitely feeling the love of our spacecraft, even though one of our spacecraft, DART, will be actually, hitting one of them. So
right.
I figure asteroids hitting Earth for a few billion years is about time that we hit back. And that's the story of DART. But anyway.
Yeah, so I think the Lucy mission is really, really cute and interesting. So the Lucy mission is the first space mission to study Trojan asteroids. For those of you who don't know what Trojan asteroids are, they are orbiting the sun in two very loose groups, with one group sort of leading ahead of Jupiter in its path and the other trailing behind. And so this fantastically planned flyby mission led by Dr. Hal Levison. And so this is going to be a flyby of one main belt and 7 Trojan asteroids. And one of that asteroid is actually a binary asteroid, which is so cool, I think. And so we're going to have close-ups of so many different types of asteroids. Different types, meaning when we take spectra of these asteroids, they show differences in their spectrum. And from that, we've been able to figure out how the composition of these asteroids are different. And so some of them can be this very dark type. And so they can resemble, the spectra can resemble something that we find in the, yes, some of the pictures is what Jason is showing.
I'm so sorry about that. Yeah, it's the world we live in, computer problems. Anyway, please, I'm so sorry to interrupt. Go ahead.
No, you're fine. And so some of these dark asteroids, you can see how, these are not exactly true color. They have been adjusted a little bit. Yeah, they're pretty dark. And so some of these Trojan asteroids look like they come from the Kuiper Belt, which are these icy bodies beyond the orbit of Neptune. But a few of them have spectra that look like there's the C-type or carbonaceous material-rich asteroids that mostly come from the outer parts of the main belt of asteroid. And so all of these Trojan asteroids are pretty dark. We think they're rich in carbon compounds. They might be even rich in water and other volatile materials. And so you can imagine that if you want to understand the history of how we got carbon and a carbon-based life and water, some of these objects would be crucial to investigate. And so, yeah, so Lucy mission is the one that that is to, I'm so excited about. And then apart from that, we have the Lucy sister mission, Psyche, which is going to asteroid Psyche. That's led by Dr. Lindy Elkins-Stanton. And that is going to a metal world, as Yes, I really love
Beautiful
this picture.
illustration.
Yes, so this has been drawn by Dr. Sarah Noble, who's also a planetary scientist, and they're trying to figure out a way to name all the features on Psyche, and they're thinking of butterflies as being butterfly names being used. So this is not confirmed yet, but yeah, this is something that they were talking about, and she drew this, which is very, very cool. But yeah, so this is one of the most bizarre, unique kind of object in our solar system that we visit. And the one last one that I want to just give a shout out to is the Janus mission, which is a small sat mission going to 2 pairs of binary asteroids. And each of these pairs behave differently. One has this pair where the moon is goes around in a chaotic orbit around its main body, whereas in the other pair, it has a very stable orbit. And so it's kind of allows us to understand the why certain objects behave in that fashion. So
very cool. A lot to look forward to for
Yes.
Small Worlds missions coming up, sounds like. Yeah. Well, let's move a little closer to home, even keep journeying inward and kick it over to Brett. I wanted to ask you about NASA's Artemis program right off the bat. And, they're planning all these robotic and crewed missions to the surface of the moon, hoping to get humans back on the moon by 2024. It remains to be seen whether that'll actually happen. But anyway, it sounds like a lot of stuff happening there. As a lunar scientist, what sort of things are you hoping these missions will teach us about the moon?
Yeah, so as you mentioned, this is a really exciting time for the moon with so many missions to the surface coming up in the near future. These will be NASA's first missions to the lunar surface since 1972, when the Apollo 17 astronauts left. And so although the United States hasn't landed any people or robots on the surface in almost 50 years, there are currently 7 planned robotic landers coming up just between now and 2024, including 2 later this year. So I don't think a lot of people realize how much is coming up and in such a short time. And then that doesn't even include the human landings of the Artemis program. So the robotic landers are going to be part of NASA's commercial lunar payload services. And this is just a totally new model for how we can explore the solar system. NASA is essentially buying a ticket to the moon from these different commercial providers, and the passengers on those rides are the scientific instruments and rovers that we can use to investigate some of these science questions that have been hanging around for the last 50 plus years, and those that we've been starting to ask along the way too. So we'll be getting so much exciting new information about the moon. And as you mentioned, the moon is, of course, much closer to home. So one of the things that I'm really excited about in the coming years is learning more about how the Earth and the moon were shaped by impact events early in their history. So, on Earth, of course, we live on this beautiful, geologically active world. But the problem with that, at least it's a problem for weird planetary geologists like me, is that the Earth's surface is constantly being refreshed by plate tectonics and weathering. So we can't look back into its very earliest history. And on the moon, we don't have those annoying issues. So we can look way back in time, see what was going on in our neighborhood about 4 billion years ago. And one of the things the moon shows us is that there was a lot going on about 4 billion years ago on the Earth. That was right about the time we think that life was beginning to emerge. But the moon's record shows us that that was a really crazy time in the solar system with huge impact events occurring that created craters over 1,000 kilometers across, like the Imbrium Basin. And so we see those on the moon, and we know that they were also forming on Earth. And when impact events like that happened on Earth, they would have vaporized the oceans, sterilized the crust down to hundreds of meters. And so working out that early kind of balance between catastrophe of these giant impacts and when they were happening and how that was affecting life just as it was beginning to emerge, is one of the coolest things that I think the moon has to offer us. And one of the things that I'm really looking forward to studying in the coming years.
It strikes me, talking, as you mentioned that, how similar the theme almost is to what Maitri was telling us about small bodies, that it really preserves this history of what was happening in our solar system. And that seems to be a major thing that planetary scientists like yourself are always trying to figure out. You're trying to unpack this history that happened early on.
Yeah, I always wish we could, rewind time backwards and be a little fly on the, I don't know, wherever, watching this all happen. But yeah, she's looking at the impact doors, and I'm only looking at the scars they've left.
And I was also going to show, as you mentioned, the Commercial Lunar Payload Services Program. Here's one of the landers that was just announced, Firefly's little lander here. And that one's, like you said, there's a couple other ones coming. There's one this year, but this one's in 2023. And because I'm going to have to plug the Planetary Society tie-in, PlanetVac will be on this mission as one of the experiments, and it's going to practice taking a little sample of lunar dust. So as Brett said, just a ton of cool things.
Really cool. It's going to vacuum up some samples that someday hopefully can use that to return them to Earth by collecting them that way.
And Brett, while we have you, since you're the deputy PI for the high resolution camera, the LROC camera, aboard the Lunar Reconnaissance Orbiter, that's kind of this mission that I think some of us take for granted. It's still up there, still doing cool science and taking beautiful images. Can you give us any update about how that mission's going and how it might support some of this upcoming activity?
Oh yeah, I hope people don't take it for granted, because it is.
I didn't want to assume. Yeah, sorry.
Spectacular mission. It's been in orbit for the past 11 years. And in that time, kind of initially started with an exploration mission, scouting out future landing sites, and then has done kind of transition to this long-term science investigation. And so we still have fuel, and the spacecraft's doing well, so it should be healthy for another future years to come. And one of the fun things that we will be doing is monitoring these landings on the moon. We've been able to take pictures. Well, first we started with the Apollo landing sites, but those are ancient, and now we've seen the surface change as other landers have come and gone. Like for Chang'e 5, we were able to take a picture of the surface before it got there, while the lander and the return vehicle were on the surface. And now we have a new picture after the return vehicle left the surface. Yes, and thank you for showing this image here. We're not just monitoring the robotic and changes that occur to the moon's surface, we're also looking at the natural changes. So while I talked about that really ancient impact record that we can get from the moon, we can also get the current impact rate by watching craters form on the moon's surface. So hopefully you can see blinking there as a before image and an after image of a 34-meter crater that formed on the moon during LRO's mission there. So the longer we go, the more of these impact craters we can keep imaging and learning how they're shaping the surface and what that population is that's in our neighborhood. Oh, and you're muted.
I did that was the classic move.
Yep.
I was just going to show everyone, our audience, here a couple examples of those awesome pictures. Can you tell us what this is?
Yeah, this is the central peak of Tycho crater, one of the bright red craters that's about 100 kilometers across on the southern near side of the moon. And I love this image because one of the things that we do, of course, we're answering all these science questions that can at times be a little esoteric, but these kinds of images, we focus on making sure we can also just capture the beauty and like the stunning vistas of the moon, so that we can all appreciate just how gorgeous this little world is. And in this image, you see this mountain on Earth. Mountains take millions of years to rise and fall. This one would have formed in just minutes as the impact event created this incredible pressure on the moon's surface, and then it rebounded back up. And so you have this mountain surrounded by molten rock that's now frozen, just showing you the real catastrophic and spectacular effects that impact craters or impact events have across the solar system.
And I should note here for our viewers, this is not the high resolution version of this picture by any means. You can zoom in on this boulder here and make it like as big as my screen here.
And if you keep zooming in, that little boulder in the middle there is the size of a football field. So you can see incredible details on the moon.
And real quick, before we move off of you, you talked about, there's the science questions, but also just the beauty that missions like this send back to Earth. And here's a great example of one of those, this Earthrise photo.
Yeah, we had to recreate this view. And I love thinking about astronauts on the surface, watching the Earth rise. What a great view that they will have.
Fantastic. I'm going to stop sharing here and kick it over to our last panelist here. Joe, you wrote about Venus in the recent planetary report I had mentioned earlier, and that was before we had this kind of bombshell discovery that scientists may, and we put may like and with all the caveats and air quotes, may have discovered phosphine, which is this chemical that's strongly related to life. And could you start by telling us a little bit about that and how Venus scientists like yourself are reacting to this news?
Yes, it's been extremely exciting for the entire Venus community. And it feels like a lifetime ago that I did write that article for you, Jason. So phosphine is a molecule, 1 phosphorus atom, 3 hydrogens. And on Earth, it's a biosignature, which means that it's a molecule that's produced by biology and not geology. So one thing I found really interesting learning about phosphine is that we don't actually know what microbe on Earth produces phosphine. As the New York Times said last week, phosphine is found in our intestines, in the feces of badgers and penguins, and in some deep sea worms. So along with exploring Venus to truly understand phosphine, I think we need to visit some badgers and penguins. But for this study that came out a few months ago, scientists searched for signs of phosphine in the atmosphere of Venus using 2 ground-based telescopes on Earth's surface that are sensitive to light in millimeter wavelengths. And in their discovery paper, they reported one spectral line that they attributed to an abundance of about 20 parts per million of phosphine in the atmosphere of Venus at altitudes of about 50 or 60 kilometers above the surface. And those altitudes are special because they are habitable. As you all probably know, the surface of Venus is hot enough to melt lead. It's a very unpleasant place to be. But 50 to 60 kilometers above the surface, there's a cloud layer that has Earth-like temperatures and Earth-like pressures. So if microbes could somehow hang out in those clouds and not sink down to the hellish surface, they could survive. So as with anything involving aliens, this claim detection has been extremely controversial. But personally, I've been very happy with the controversy because all the scientists involved are behaving with humility while being very honest and not being afraid to make very rigorous scientific arguments. So it's been a great discussion to have. There's some technical issues with the data collection that might reduce the statistical significance of the spectral feature that could be phosphine. There's also another gas, sulfur dioxide, that is known to be in the atmosphere of Venus, and it could possibly produce a similar spectral feature. So there's a lot more work that needs to be done to understand if there's phosphine in the atmosphere. And in reality, we're not going to know whether there's phosphine or not until we go there. But the most important thing about phosphine is that it reminds us all that Venus could have been a habitable planet for billions of years, for most of its history, and for far longer than other worlds in our inner solar system like Mars. So we know that Venus is not a nice place today, but more than 1 billion years ago, it could have had oceans just like Earth, and we simply don't know whether or not that's been true. And if Venus ever did have oceans, it makes it far more likely that life was able to evolve as the oceans went away into the one remaining habitable niche on the planet. So I think that the phosphine detection has really reinvigorated interest in studying Venus. Right after this paper came out, Jim Bridenstine, who's then the administrator of NASA, responded on Twitter by saying that it's time to prioritize Venus, and I could not agree with him.
I can totally understand why you'd feel that way as a Venus scientist, and I'm right there with you. I want to see some missions there soon. Well, speaking of missions there, as we were just saying, Venus unfortunately doesn't get a lot of missions, or at least it hasn't gotten any U.S. missions for quite a long time. Since the 90s was the last time NASA sent a mission there. We do have Japan's Akatsuki probe is there now doing it's studying, I believe, the cloud layers, and maybe you can mention that a little bit. India is launching a probe there as well, an orbiter there. And there's a possibility that NASA maybe has a couple missions they have to pick from their next line of, it's either Discovery or New Frontiers. I can't remember off the top of my head. So anyway, what are some of these big questions that you would like to see missions answered there? And like, what are some of the missions that we could send there?
Yeah, so Jason, like you said, the last mission that studied the surface geology of Venus was Magellan. And Magellan entered orbit around Venus when I was 10 days old. So for my entire lifetime, the last 30 years, we've had to rely on these super old school maps of Venus. And there have been just really basic first order questions, like appallingly first order questions that we're ignorant about. So like I said, I think the first big question is, did Venus ever have oceans? And to answer that question, we need to I'm switching microphones on the advice of one of my panelists. Hopefully this is a lot better. Sorry about that. So the first big science question we need to answer is whether or not Venus ever had oceans. And the way to do that, there's two different ways. One way is to peer through these clouds of Venus that you're showing using radar that we can actually use to image the surface. And we can also look through the atmosphere in a few special spectral windows in the infrared. And we want to know if these enigmatic geologic terrain on Venus called tesserae, if they're made out of granitic rocks like Earth's continents. It's believed that the reason we have continents on Earth is because we have oceans. So if Venus has continent analogs, that might be a sign that when they formed, there were also oceans. We also want to measure the isotopes of noble gases in the atmosphere of Venus, which are these special elements like xenon and krypton and argon and neon, and they can give us clues about the primordial material that formed Venus and tell us if Venus accreted with similar amounts of volatile material like water than Earth did. The second big question for Venus that we need a new mission to address is whether or not Venus suffered a cataclysmic geologic transition. So when the Magellan mission collected the first global radar maps of the surface, one of the main discoveries was that there were only 1,000 impact craters on Venus, and their latitude and longitude coordinates are randomly distributed. So some scientists have argued that Venus was entirely resurfaced by volcanoes over a short geologic time period called catastrophic resurfacing. And this might have been when Venus lost its habitability. All the oceans evaporated. And so we need new geologic maps to actually figure out what the different geologic terrains are on Venus, figure out how old they are with respect to each other, and figure out if this catastrophic resurfacing ever happened. So 2 out of the 4 missions that are the finalists for the NASA Discovery Program, the next just under $1 billion mission, would address these science goals for Venus. I'm not on either of the mission teams, so I'll say very nice things about both of them. So there's Veritas, which would be the next generation successor to Magellan. It would collect high resolution global radar maps of the surface, and it would measure the rock types using these infrared spectral windows from orbit. And Da Vinci Plus has a smaller orbiter, but also a deep atmospheric probe. And the probe would be extremely exciting because it would measure those noble gases that I talked about, and would also take great images of one of these special tessera terrain on Venus and collect very detailed constraints on its geologic structure and on its composition. So I think Venus scientists, our request to NASA is basically to pick any mission. There's too many science goals about Venus that we want to know for a single mission to address, but any new mission would give us very powerful insights and really help unravel the mysteries of Earth's evil twin.
That's fantastic. Well, I hope, you know, every world is cool and worth exploring, but I hope that some way we find a way to see another Venus mission soon. If only there were enough money to go to all the places all the time. So we have about 15 minutes left in the session here, and I wanted to do one more quick lightning round with all of you. And with just 15 minutes left, I'm wondering if we should also kind of combine that with the audience Q&A, if that would kind of be all right with all of you. So I was going to ask each of you if you had one wish granted for each region of the solar system you study. What would it be? Would it be a scientific question you really want to answer, or a mission you'd love to see, or anything else related? So Deepak, how about I kick it to you first to answer that wish list question? And while you're at it, if I could get you to sneak in a second answer, one of the audience questions was, is Europa's iron core solid, and is a magnetic field vital for life? And I don't know if you can get both of those quick, but I'll be quiet and let you see what you can do.
Well, my wish list is pretty much what you said before, Jason. There's so much real estate in our solar system and beyond. You know, we have cosmologists that are looking even further, right? And everything has such, we can learn from so many of these things, and it's so hard that we have such a small bucket of money to explore all these places. And that's why places like the Planetary Society exists, and all of you members help us to try to advocate for getting that extra funding for all these wonderful places. I'd love for Venus to be explored. There's a couple other, as we talked about, there's in the Discovery round, there's a mission that's proposed that could be going to Triton. That's one of the other ocean worlds around Neptune. And there's another one that's being proposed that'll go to Io, which will teach us more about the moons of Jupiter and tidal heating and how these energies could possibly sustain life. So, you know, all of these things are incredibly compelling, and if only we had enough money. Interior of Europa. Actually, so what I showed you was a notional design. It was a solid core. That's what we think is there, but we don't know. That's why we're going there, and we're going to find out. And sorry, Jason, what was that last question?
That was it about the iron core. But we also, while you're at it, we had that other question about planetary protection, and that one very much kind of pertains to you. So might as well throw that in too.
Yeah, we're talking about these places where life could possibly exist. And what would be completely disastrous is if we brought a spacecraft to a place where life could possibly exist, and there were microbes on there that infected that life, and you know that would be horrible. We don't want to do that. Plus, you know, that's from an altruistic standpoint. From a more selfish standpoint, we don't want to introduce life to a place only for a future mission to discover the life that we introduced. You know, then we wouldn't know whether that was completely indigenous or not. So we need to make sure we don't bring ride-alongs and stowaways. So what we do, and one of the things that we're doing with Clipper, is what we call sterilization, and it is what it sounds like. So we actually have to make our spacecraft with all components that we could take up to a high enough temperature to basically bake off everything. So we sterilize all of our hardware, and this costs a lot of money because we have to take them to temperatures that we don't normally have to operate our equipment in. So it's an engineering challenge to make that work. And then once we know that we have a fully sterile spacecraft, throughout the entire process on the ground, we have to make sure we maintain that level of sterility. So we're talking bunny suits on top of bunny suits on top of bunny suits. It's a lot of effort and a lot of added burden on the ground, but you know, ultimately we don't want to carry any germs with us out to space. So that's what we have to do. So hopefully that answers the question. Thank you.
Thank you, Deepak. Let's move back to my three at this point. And I do have a small bodies question here that you might be able to answer in addition to telling us what would be your dream for an upcoming mission or a science question to get answered. Someone in the audience asked, are there missions being developed for a visit to Jupiter's Trojan asteroids? You had mentioned the Lucy mission, but they also asked, do we expect to see any differences between them and asteroids in the main belt? And I think you touched on that a little, but maybe you could just kind of clarify that as well.
Yes. So in terms of, you know, one wish, I wish I had more than one wish, just because there's so many small body types to visit, right? So I just want to talk about two wishes that, if granted, would be amazing. The first one is mission to the largest asteroid, which is Ceres, which we think is a differentiated small body. So it's about 1,000 kilometers in size. Very, very dark, because the surface we think is very rich in carbon, very specifically graphite. And the Dawn mission in 2015 found these very whitish stuff on its surface. Like the bottom of the craters, some of these craters had this white, it's actually salt. It's sodium chloride, table salt, sodium carbonate. So some of these salts that were found. And so I think a mission to Ceres would be amazing, specific mission to Ceres, and maybe bringing back some of these samples, because through meteorite studies, we know that some of the carbon, so some meteorites contain salts, and those salts are filled with either water or carbon. And so we can study, the intrinsic carbon in the water from some of these meteorite bodies, and we can understand how they formed and what that body looked like. So taking that analogy, we can understand more about Ceres. So first wish would be a mission to Ceres to understand the largest asteroid. The second one would be more of it could be observational through the new Rubin Observatory that's coming up, which will discover 10,000 objects every month. And so we will know a lot about the Jupiter Trojans, but we don't really know much about the Saturnian and the Uranian and the Neptunian Trojan population. And if some of these small bodies in the outer part of our solar system, we think have undergone much less alteration. So more primordial, more pristine than some of the other stuff that we have in our collection. So if we can sort of study them either through observatories that are coming up or through flyby missions, that would be amazing too. So 2 wishes, sorry.
That's okay. That's all right. And real quick, any differences between the Jupiter Trojans and the asteroid belt asteroids, main differences?
Yeah. So there is, we know of compositional differences between the main belt asteroids and the Trojan asteroids. But of course, a lot of these bodies are constantly being tugged towards the sun, right? So they move around, and we know now that actually the spectra can change as a result of their movement towards the sun. Like Bennu has already taught us that this can happen, where you're changing the composition.
Okay, fascinating. Well, I'm looking forward to all of those wishes getting fulfilled, or hoping they will one day. Brett, let's go back to you. I'll ask you for your wish list. And then also someone asked, how confident can we really be about the water detection at lunar poles? And they said prior to the time when somebody is holding a glass of it. And so that's a whole can of worms, probably, but maybe you could talk quickly about that as well.
Sure, yeah. So my wish is easy. I'd love to see Artemis Base Camp on the moon. A real program of human and robotic exploration on the moon surface, people there for extended stays, learning to live and work on another world. And the kinds of both sophisticated science questions we can answer when you really have people there able to dig in literally, and then just how that will enable exploration out into other worlds, including Mars, is something I'm hopeful and looking forward to seeing. And then, yes, in terms of another thing that can enable future exploration, water at the moon's poles. We are definitely very confident that there is water at the moon's poles. There is much less certainty about how much water is at the poles, what its distribution is, and how easy it is to get to in terms of mining it and refining it down to a point where you will have that glass of water in your hand. Because really all of our studies so far have been from orbit or just at a single pinpoint on the map. The L-Cross experiment crashed into the moon. The ejecta that came up had about 5% water in it. So we know in that one spot, and there's water, but we don't know how deep is it buried under the surface or how continuous is it. And so understanding if those resources are really something that we can use as a valuable reserve to mine. That is the real question that we are working on answering next. And the first step in that is the Viper mission, which will be a rover exploring shadowed regions at the South Pole in a couple of years.
Really cool. Yeah, I can't wait to see a rover checking out areas of the moon that never get sunlight.
So yeah, that'll be
Super cool concept. Yeah. And Joe, with just the 5 minutes we have left, if we can round it out with you again, maybe you could tell us about your Venus wish. I mean, it sounds like you just want a mission. You just you want a spacecraft to go again. But also someone had asked for clarification about the altitude above Venus's surface that may be able to support life. And maybe you could talk a little bit about that as well.
Yeah. So of course, my two wishes are to explode Mars so that the rest of the solar system will get more attention. And the second wish would be for a cosmic hairdryer so we can blow away that pesky atmosphere and look at the Venus rocks better. But in that pesky atmosphere, yeah, the magic range for Earth-like temperatures is somewhere between like 52 and 70 kilometers above the surface. The surface of Venus, it's more like being under the ocean in Earth than being under a gas atmosphere. The surface pressure is 90 bar, 90 times Earth's surface pressure. It's hazy, like an extremely cloudy day, but there's still some sunlight that filters down. And again, the temperature is hot enough to melt lead. So if you were teleported there, you would sort of instantly vaporize. Not very pleasant. But if you could stay up in the clouds where the temperatures are Earth-like, all you have to worry about is the fact that the clouds are made out of sulfuric acid. But other than that,
No
it's
big
a very
deal.
benign environment. Yeah.
So that's interesting. So could you, like as a person there, if I were to go there, could I fly around in the clouds and just step outside? I mean, besides the sulfuric acid thing, I guess.
So neither, like I said, the Discovery missions that are finalists right now feature an orbiter and then an orbiter plus a deep atmosphere probe. At the New Frontiers level and flagship level, you can start flying balloons in the Venusian atmosphere. And these are great scientific platforms because you can make these measurements of the noble gases, phosphine, the cloud particles. You can really spend a lot of time making very careful measurements, and you can make those measurements in different places. And those balloons can survive for like 2 Earth months or so. And we're exploring right now concepts where you could dip the balloon below or drop a camera off the side or lower a tether down and actually peek below the clouds and thus study the surface. So while I personally wouldn't want to volunteer to be an astronaut, exposing my fleshy, fragile human self to the elements in the Venus clouds, I would love to send a little robot on a balloon and have that robot take amazing science data.
Awesome. Well, thank you for that answer. Yeah, I would love to see that too. And also, Joe, I need to mention you win for having the cat appearance and for the Planetary Society T-shirt I recognize there. So if you had that on your bingo boxes, everyone, between me getting bad audio, yeah, you all won. So. Well, thank you very much, all 4 of you, for joining me today. And yeah, Jessica, do I need to kick it back over to you to say any closing words on the panel?
Yeah, thanks so much, Jason. And thank you to all of our speakers today for sharing their expertise with us. Really, really amazing content. While you get moving on to the next panel, we are doing a next panel on the science of Mars. You can get there by clicking on agenda to the far left and choosing the session title to get connected. And also please visit the exhibitor area to meet this year's Planet Fest supporters. Click on exhibitors in the far left menu to take a peek. Thank you all so much for being here.
Thank you.